For post-tutorial quiz 1, I have decided to do problem 14.P.48, where it asks me to determine the distance between a location X and a proton or electron, where a helium nucleus is located 1 times 10 to the negative 10 meters away. This requires me to use my knowledge of the superposition principle, as well as my knowledge of calculating the electric field of point charges. So I started out with the diagram to represent the situation. Here is a proton and a helium nucleus with respect to the location X, which I set to be the origin. Both of these particles are positively charged. The helium nucleus contains 2 positively charged protons and 2 neutrally charged neutrons, which have a net charge of plus 2e. And the proton, we know, has a charge of plus e. So that means the electric field due to these particles will be pointing out from the particle towards location X. And in this case, these electric fields are the electric fields due to the proton and the helium nucleus. And according to the superposition principle, the net electric field is the vector sum of all the individual electric fields due to the other particles surrounding the area. We are told that the net electric field of these particles must be equal to 0. When you rearrange this equation, you find that the electric field of the proton will be the negative electric field of the helium nucleus. I can calculate the electric field due to the helium nucleus because I know how far it is away from location X. And I can use the formula for the electric field of a point charge to calculate its electric field, which is shown here as being 1 over 4 pi e naught times its charge, which in this case the charge of the helium nucleus is 2e, over the magnitude of r squared times r hat. The vector r is equal to the r observation location minus r source. And in this diagram, r observation location is equal to 0, 0, 0 meters, and our source is equal to negative 1.0 times 10 to the negative 10 meters, 0, 0. Using this observation and source location, you get that r is equal to 1.0 times 10 to the negative 10, 0, 0 meters. Then the magnitude of r is equal to the square root of r squared, which is 1.0 times 10 to the negative 10 meters. Then to find r hat, or its direction, you take the vector quantity of r divided by its magnitude, and you get the direction to be 1, 0, 0. Then when you use these values in the equation for a point charge, you get that the electric field of the helium nucleus is equal to 2.88 times 10 to the 11, 0, 0 newtons per coulomb. As I've said before, the electric field of the proton is equal to the negative electric field due to the helium nucleus, since the net electric field is 0. So the electric field on the proton will be negative 2.88 times 10 to the 11, 0, 0 newtons per coulomb, which written in magnitude times direction is 2.88 times 10 to the 11, 0, 0 newtons per coulomb times negative 1, 0, 0. By knowing the magnitude of the electric field of the proton, I can use it to solve for the magnitude of r. So by using the electric field point charge equation, I can solve for the magnitude of r in this process. By solving, I find that the magnitude of r is equal to 7.07 times 10 to the negative 11 meters. So the proton is located at 7.07 times 10 to the negative 11, 0, 0 meters, or 7.07 times 10 to the negative 11 meters away from X. Here's a diagram of where the electron will be located with respect to location X when H is in the same place. Here, the electron has a negative charge of negative E, so the electric field on the electron will be pointing towards the particle. Using the superposition principle, we know that the electric field due to the helium nucleus will be the same as it was from the previous calculation. The electron won't block the electric field of the helium nucleus, so the electric field due to the helium nucleus is still 2.88 times 10 to the 11 00 newtons per coulomb. Since the net electric field still has to be 0, we still know that the electric field from the electron will be the negative electric field due to the helium, so therefore the electric field due to the electron must have an electric field of negative 2.88 times 10 to the 11 00 newtons per coulomb. And we can use the magnitude of the electric field due to the electron, which is 2.88 times 10 to the 11 newtons per coulomb, in order to find the magnitude of R by using the equation for the electric field of a point charge, as shown here. And we get that the magnitude of R is equal to 7.07 times 10 to the negative 11 meters. But this is only the magnitude of R. The electron will actually be placed at negative 7.07 times 10 to the negative 11 00 meters, instead of the 7.07 times 10 to the 11 00 meters, as shown in my diagram. This is due to the electric field pointing away from location X but towards the electron. So overall, I found that the electron will be placed at 7.07 times 10 to the negative 11 meters to the left of location X, while the proton will be placed 7.07 times 10 to the negative 11 meters to the right of location X, when the helium atom is located at 1.0 times 10 to the negative 10 meters to the left of the origin.